we defined a programming language for the formation of skills that allow the expression of common and important tasks. I encourage you to read our Try 2017 paper for more details about the language and the kind of tasks that can be expressed in it. RobotIST builds on the same language and allows the expression of the same tasks. It additionally incorporates feedback to the programmer. Like many other robot programming systems, the situated tangible programming system we originally built did not provide any feedback, neither during creation of the programs nor during execution of them. Using it was like coding in a simple text editor without any of the common IDE features and without any means of debugging the program. Issues were discovered only after the execution of a program, and we could only guess about what could have gone wrong. As testing robot programs is costly and challenging, this was very undesired. In RobotIST, we looked into the use of feedback in the physical space and what it would mean for tangible programming tools. We were particularly interested in feedback around robust understanding of the environment, semantics of programs, and programming errors, which are important for both creation and execution and debugging of programs. In fact, the last one, debugging, has rarely been the topic of research in the broader area of tangible programming. So we consider our work as an early exploration in this space as well. RobotIST offers the following features. It provides feedback about robust understanding of the different instructions. This makes it easier to learn the language of our tool and use it to express manipulation tasks. It also provides a pathway to program verification and supports debugging. And as there is now less guesswork in terms of understanding robots' internal logic of the program. Moreover, such feedback makes it easier to reason about the necessary changes to a program. For example, when editing an existing program or when errors arise. RobotIST presents robots' perception of the environment to the programmer. This makes the programmer more confident in referencing objects and locations in creating programs. For example, because inaccuracies in environment perception are clearly demonstrated in the physical space, right where the program exists. It also supports debugging, as the programmer has explicit information about what the robot sees and what it does not see. I'd like to emphasize that these features are relevant broadly and beyond situated tangible programming. The support provided by the existing traditional text-based systems or the newer visual programming tools with regard to these features are inadequate. But how does RobotIST realize these features? Let's walk through creating a program to get a better sense. When we start a system, we see something like this. We see the boundary of robot's workspace is highlighted to help the programmer better understand where is visible and reachable to the robot. We refer to it as workspace projections. This type of feedback helps the programmer better understand the limits of robot's perception and actuation ability and avoid providing instructions that are impossible for the robot to see or do. We also see the objects that robot has detected are highlighted to make robot's perception of the environment transparent to the programmer. If something has not been detected, referencing it during program creation would fail. If the detection is larger or smaller than the actual size of the object, the robot would not be able to properly grasp it. All this information is readily available to the programmer through environment perception projections and make it less likely to encounter errors during program creation or at runtime. Tangible blocks are also highlighted so the programmer knows that the robot sees them. If the robot misses a block and behaves in unexpected ways, the programmer would know, as no highlighting appears. Similarly, these block projections help programmers better understand the cause of errors. Assume we want to create a program to stack all green cylinders at a certain location. The instructions shown here should achieve that. We select the cylinder by pointing an object selector to it and instructing the robot to pick it up wherever it finds it. We have also specified the location where the cylinder should be placed at by providing a location selector that points to that place. As the system loops through our program, all green cylinders are stacked at the specified location. RobotIST helps us understand the semantics of this program in multiple ways. We see all the blocks forming one instruction are similarly colored to signify their relation. For example, the arrow selection block, as well as the action and ordering blocks, are all in pink. We also see the object referenced by the arrow is highlighted in the same color. In fact, objects of the same type are similarly colored, as the instruction selects all green cylinders as potential targets for pickup. Similarly, the blocks within the second instruction are highlighted in the same color. The location identified by the instruction is represented by a crosshair of the same color as well. These instruction projections allow the programmer to verify whether her or his intent is properly expressed in the program. This simplifies learning and use of the instructions and would facilitate reasoning about what instructions are relevant to a certain goal, which is useful for both creating programs and debugging them. What you see on the left on this slide is what one would get in our original situated tangible programming system. I hope comparing it side by side with RobotIST on the right convinces you of the importance and usefulness of feedback. Now, what happens if there are errors? RobotIST highlights in red where the error is. For example, if one type of block is missing and the robot cannot form an instruction, the other two are highlighted in red. If the object is missing, the location considered to find it is highlighted in red, in addition to all the blocks of the instruction missing that object. Instructions are all highlighted in red if they appear out of order. For example, when a place instruction comes before a pick instruction, as shown here. Overall, these error projections help the programmer find where something is wrong. In some sense, they are the physical world equivalent of the red squiggly lines in text-based IDEs. There is also the possibility of getting more information about an error by pointing the probe block where the error has been identified. By doing so, we get information on demand at the bottom of the workspace in the physical world equivalent of a status bar. For example, in the image shown here, we get the message that action block is missing. This is sort of the spatial equivalent of navigating errors by hovering over them to get information about the cause. Now that we have a program, we can execute it. But what kind of feedback would be relevant at runtime? RobotIST highlights locations and objects relevant to each instruction of the program in a different color. Seeing a crosshair somewhere, the programmer knows the robot would do something there. Also, highlighting objects relevant to the program signifies that the robot would manipulate them in some way. Overall, these program projections, based on the semantics of a program, help the programmer better reason about what robot is doing in relation to the program. RobotIST additionally changes the style of projections on an object or at a location when the robot is about to manipulate that object or location. These execution projections make the execution more transparent to the programmer. Error projections similarly identify where something is wrong. For example, if the robot cannot reach the object, it highlights it in red. If it cannot find the object at all, it shows where it looked for it. Probing is similarly available to get on-demand information about the error. We implemented RobotIST for a PR2 robot within the framework of Robot Operating System, or ROS for short. This image shows the overall architecture of our system. There are 3 modes of operation. In the idle mode, the RGBD feed of a Kinect camera mounted on robot's head is processed to detect tangible blocks and to segment objects and surfaces of the environment. This information is passed to the projection node to be visualized using a head-mounted projector. In the programming mode, information about tangible blocks and objects is sent to the compilation node that groups them into instructions and sends the information about these instructions as well as information about the environment and any errors associated with them to the projection node. In the execution mode, tangible blocks and objects detected in the environment are sent to the execution node, which also obtains the instructions of a saved program and generates necessary robot movements. The execution node also communicates the information about the environment, the program, and errors to the projection node. We did an observational study to better understand if RobotIST features are actually used as intended. If so, we have a good reason for doing a comparative study that more rigorously evaluates how successful the system is in achieving its goal. So our objective was to observe how people use our system, and particularly the projection features. RobotIST addresses important issues in robot programming and is beneficial to both novice and expert robot programmers. In this preliminary observation, we focused on the value our system offers to expert users. So we recruited 8 robot programmers from our department. Given none of our participants had prior experience with situated tangible programming, we gave them a short tutorial that took between 5 and 10 minutes. We then asked them to create a program for the stacking task illustrated earlier. While simple, this task is very common in industrial settings and shares important aspects of other common tasks in these settings. At the end, we invited participants to share their thoughts and experience using your system in a follow-up questionnaire. All of our participants created the stacking task successfully between 4 and 8 minutes, with the average time of 6.5 minutes. Considering the short training time, completing this task in this amount of time is noteworthy. Our participants found situatedness of both input and feedback helpful. Situated input is a feature of situated tangible programming paradigm, so we further probed the other aspect of participants' experience around situated feedback. Our participants found workspace projections, environment perception projections, and block projections helpful in having a more clear understanding of robots' capabilities and what it sees. They explicitly described this as helpful for debugging. For example, one participant said, "I was able to debug my program when it could not see a certain block." Instruction projections successfully communicated the semantics of programs and helped participants more easily express their intent, as nicely summarized in this comment. This was especially useful in the scenario that uses disobject blocks, since it shows that the robot did extrapolate that I meant for it to see multiple instances of a specific kind of object. Error projections were particularly helpful in debugging. For example, one participant described it as very helpful, since I was able to see what exactly was the issue with the program instead of having to guess. The probing feature was also praised in comments like, I liked how this could give me an error about a specific part of the program, which let me march through errors. While encouraging, this was just a preliminary evaluation, and we need to do a more rigorous study comparing RobotIST with visual programming and text-based interfaces. There are also limitations with our specific implementation of the idea. Some objects and tangible blocks are invisible if they are blocked by other objects when we use head-mounted camera. Similarly, some objects block projections on others when we use head-mounted projector. Overhead sensing and projection might mitigate some of these issues, so does rear sensing and projection. We should also explore other sensing technologies, such as RFID tags instead of AR tags, to allow the detection of tangible blocks. This would allow us to reduce the overall lighting that enables sharper projections. Currently, common but simple tasks can be expressed in the tangible programming language underlying RobotIST. We should further explore how complex the language can become before situatedness cannot add value. As is common in many programming systems, we should strike a trade-off between easiness of use and expressive power. And all of these can be the topic of further research in future. To summarize, robot programming has unique requirements, such as establishing the correspondence between the physical world and robot's internal representation of it, which RobotIST addresses. This system provides feedback within the physical space to communicate the semantics of programs and to display robots' understanding of the environment. With these provisions, it better supports learning and use of the program semantics and facilitates debugging. With this, I conclude my talk, and I'm happy to take on any questions.
Much. We have a lot of time for questions, so.
To me, the most useful thing here seems to be the projection. That's sort of something you don't get in the real world, and you're adding that, and that the other parts could be accomplished by using just the video stream and selecting or using some sort of on-screen manipulation. Can you comment on sort of what they really liked about the manipulating the tangible specifically? Because I see sort of other issues, like you can't do 3D things and things like that very easily.
So we haven't done any sort of comparison with other programming interfaces like the visual interfaces that allow you to just see. But there are many issues with like trying to bring in the 3D world on a 2D screen. And a lot of the times you have to change your viewpoint, move up and down, which is not the case when you're in the space in front of the robot and you just place these objects in the environment and the robot can easily detect them. Even if like there are good tools that allow you to navigate the 3D space on your TV screen, there is still a mismatch between what you see and what is actually there. And using the tangible blocks allows you to basically close that gap because you're where the robot is.
I don't understand. We can talk about this later, but why there would be a mismatch? Because you're seeing what
because
the robot is seeing.
you're actually mapping the points in the physical space to the points on the screen. And if you're, for example, having a ray that goes from any point on the screen to the physical space, there are multiple locations. And you have to basically disambiguate what location you're exactly looking at.
Yeah, I'm not exactly following. We can talk about it later.
Sure.
We still have time for questions. Okay, I have one. It's in your talk and in your system, you're talking all about objects and positions, and you are representing them. What's with movable object or something which is on a band? in a production state. Do you have some solution for representing them when programming so that the robot take the object exactly at a specific moment?
To rephrase your question, you're asking what happens if the object that the robot needs to manipulate moves, right? So because there are two modes of operation in our system, the programming mode and the execution mode, during programming you can just instruct the robot to basically pick up that object. And what happens at the execution is that as soon as it identifies the object, it's going to move for it. We haven't yet considered this sort of cases, but the language allows the expression of the task. It's just whether the movements can adjust for the moving object or not.
So you're simply specifying grasp this object, and the robot is kind of allowed to find out how to do it.
Yeah.
Okay, thanks. Okay, if there's no further question, let's thanks our talk again.
Thank you.